All right, taking a quick look at number 3. Notice that you're given a position equation, closed interval. The question asks you at what time is the particle farthest to the left. That's an absolute minimum. That's going to be a t-chart with the endpoints of 0 and 2 pi and any other critical numbers. Well, notice the comparison here. You're given a position equation, whereas in problem 1, you're given a velocity equation. For you to determine what else goes in your candidate column, your T column, you need to actually go through and find the derivative of that position equation. In order to do so, notice what's going to have to take place. You're going to have to use the product rule, where this is your first factor and sine of t is your second factor. All right, so you're going to have a little bit of work to do on number 3 before you can actually fill in your t-chart. You're going to have to use the product rule to find the derivative. Once you get that, type that into y1 and find the x-intercepts on this x-min to this x-max. Okay, and once that's done, then you can jump back into the t-chart and perhaps use the fundamental thermocalculus to help you find the greatest position. Or I guess no, in this case it's the least position, the smallest answer. All right, so not all problems are the same. You have to kind of think about what they give you and then how to proceed from there. All right, let's look at number 4 real quick before I turn over to the back and do some other problems on the back. All right, we're going to compare and contrast, I think, some velocities here. We have rocket A and rocket B. Actually, this is not an absolute extrema problem. It's kind of displaced in here. You're going to have to use the fundamental thermocalculus to compare the two velocity values on this one. So I don't think there's a t-chart that's necessary here. It's not absolute extrema, but it does require you to use the FTC. So let's turn it over and look at the back. We're going to take a look at question number 5. It's the question about the sand and about the beach and how sand is being removed and how it's being replaced. We're given 2 rate equations. Again, one for the addition rate and one for the removal rate. We have a closed interval. We have an initial condition. We know how much sand is on the beach at time equals 0. I don't see any indication of a particular letter that represents the sand, so I guess maybe I would just use beach. V of 0 equals 2500. I have an R and an S for removal and for addition. All right, so the question is, at what time is the amount of sand on the beach a minimum, and what is the minimum value? Again, you might need some notebook paper, but it is going to set up to be a t-chart. Okay, what is the minimum value? So I am looking for the smallest V of t value. We know we're going to have 0 and 6. Okay, again, we're looking for any other time that suggests that we have a minimum. So the graph was not provided this year, so be very, very careful. You're going to enter each of these equations into y1, y2, and you're going to look for an intersection. You're actually going to look for where the removal rate is above the addition rate. So y1, y2, x min, x max. Set a good viewing window. Make sure you're in radian mode for this trigonometric function. Make sure you see this is 4 pi. So it's very, very important that you kind of, pause and make sure that when you set these equations into the calculator that they look identical to what you have here. All right, so we're looking for another minimum value. That's going to be when your removal rate is higher than your addition rate. So where is this graph above this graph right here? So you might want to pause and do all that calculator work and then return to the video. All right, well, it appeared from my graph there was one time at which the removal rate was above, or one time when where I have an intersection between the 2 rates. And I'm going to put almost at the end, 5.11787. So now I'm going to have to go back through and calculate these values. Well, that was the initial condition. I'll probably jump down here and do this work right here with the fundamental theorem. So the amount of sand on the beach at that time is equal to how much sand was there to begin with, plus any changes from 0 to that time. All right, we want to use all the decimals we possibly can, at minimum 5 for a limit. Okay. And then I want to integrate the removal. Excuse me, I want to integrate the addition, and then I'm going to subtract the removal rate. All right, and you can do this all in one integral, or you could, part it out if you wanted to. You're going to get that value, and then you're also going to come and find the value at 6. So it sets up to be very similar to the last problem that we did. I'll just leave that for you guys to conclude. All right, let's take in a peek in at another problem here. Let's look at 7, because it sets up to be something a little bit different than what we've seen so far. Okay. I don't happen to have the graph here. It didn't transfer over on this Word document. So let me see if I can try and recreate it. All right. So we have this graph. Okay, we're told it's the graph of F. Okay, and then we're told that there's this connection between G and F, and we can see now through our practice with the second FTC that the connection is that if I differentiate both sides, it's the shortcut. I know that G prime, that derivative is 1, replace in here. G prime is actually F of X. So this isn't really F anymore, now it's G prime. All right, so we're going to find the absolute minimum value of G on the closed interval. So not this graph, but the original graph. Let's find the lowest spot that it could be at. Well, I mean, if you just kind of reason through this, we know that if this is the slope graph, that G is decreasing until you get to -4, and then it starts to increase, okay, until you get to 3, and then it starts to decrease again. So the graph is decreasing until it gets here, and then it starts to increase for a long time, and then it decreases a little bit. And if it's asking me to find the absolute minimum value, okay, I'm thinking that it decreased here, and then it went up from there and just came down a little bit. I'm thinking this endpoint is going to be the absolute minimum, but our work will justify that. So let's see how this sets up a little bit differently than the previous ones we've done. All right, absolute minimum, T-chart. There you go, closed interval. We have X's. Absolute minimum value of G, not F, so G of X. So it looks like -5 and 4. Also, any other critical numbers? Well, thank goodness we're back to just one derivative graph, as opposed to the last couple of examples we did where we had 2 rate graphs to look for intersections. Well, now that we're back to one rate graph, all we're doing is looking for x-intercepts, and minimums would be where the slope graph goes from negative to positive. So from negative to positive, that would be here. 1, 2, 3, 4, -4. All right, let's find G of -5, G of 4, and G of -4. Okay, well, for us to find G of -5, I need a G equation. And what I see up here is this. Through all this mess, if I were to replace x with -5, then the lower limit would be -3, the upper limit would be -5. Now that I no longer have a variable x as a limit, I can switch this to x. You don't have to. All right, if I can just find the value of this integral, I'll have the answer for G of -5. Well, this just indicates, let's find the area from the curve to the x-axis from -3 to 5. So 1, 2, here's -3, -4, here's -5. Okay, and notice that the lower limit is actually bigger than the upper limit. So with our properties of integrals, I could switch and put the smaller -5 down here and the larger -3 up here. All right, so we know it's going to be the opposite of whatever this is right here. Well, when you look at the picture from -3 to -5, or now -5 to -3, we have this area to -4, and then we also have this area right here. Well, the value of this integral is negative, the value of this integral is positive, doesn't matter what it is. I could calculate it using the geometric formula for a triangle, but they're going to offset. So it's just going to be 0. All right, so now we have a starting place. So we know that the point on the g-graph at -5 is 0. And we know it's just going to decrease a little bit and then increase. All right, let's go ahead and find the value at -4. I'm going to jump down here and find this one next. All right, well, g of -4, go back to the g equation. Again, you want to reverse your limits, making the answer negative. All right, so what's the value of the integral from -4 to -3? And so we're talking about this space right here. Okay, and so it's area equals 1/2 base times height. So the base is 1, the height is 2, so that would be 1. So the value of the integral is 1. However, we're going to find the opposite, so that answer is -1. So g of -4 is -1. And we knew it should be less because the rate graph is underneath the x-axis, so that means g is decreasing, so it had to decrease from 0. All right, now I'm going to assume over here at g of 4 that I've increased so much, and that area indicates that I have, that shouldn't be a minimum. Okay? But that's the next thing for us to find, to verify the absolute minimum occurs at x equals -4. All right, I'm just going to start from -4. So g of 4 equals, let's go, g of -4 plus any changes that occur from -4 to 4 from the graph of f to the x-axis. All right, so g of -4 was -1 plus, now I need to concentrate my efforts on finding this, so from -4 to 4. All right, well, -4 is here. I knew that this was 1. I could find the area in this trapezoid. I need to find the area under this semicircle. Ooh, come back. Okay, and I'm noticing here, okay, to kind of give myself a little break here, I noticed that this area is going to cancel with this area right here, or these two integrals will offset each other. So really all I need to do is find the area in this trapezoid, add it to 1, and add the area underneath this semicircle. I say that's all I need to do. I know that's a lot of work, but I mean, it's doable. All right, so g of -4 was -1, so from -4 over, well, from -4 to -3, that's 1 plus, this is a trapezoid, here are the bases, and the height between the two bases is 3. I have a base of 1 and a base of 2. Those are the y values. Plus, consider this a rectangle here. A rectangle that's 2 by 1, so that area is 2. But I need to subtract the area in the semicircle. And the area in the semicircle is pi r squared divided by 2. So the radius of the semicircle is 1. All right, so it looks like these two are going to cancel. This is 3 times, this is 9 halves plus 2 more, so 4.5. 3 times 3 is 9, 9 halves. 4.5 plus 2 is 6.5 minus a half pi, pi over 2. And remember, we're looking for a minimum. We're looking for the smallest y value. 0 is not the smallest, neither is this positive number. Rather, -1 is the smallest. Your work supports it. All you have to do is just restate the obvious, that you knew that y equals -1 when x equals -4. The remaining problems on the back also deal with absolute extrema. They may have some little different, situations to think about and deal with, but still the same kind of skill as far as the T-charts are concerned.